In this video, you'll learn how to use the sine function to solve for missing side lengths, missing angle measurements, and the area of oblique triangles. To get started, I've got a question for you to consider. What do the Pythagorean theorem and the trigonometric ratios have in common? Go ahead, take a second and think about it. Did it occur to you that these rules can only be used to solve right triangles? It's true that we have solved a lot of different types of problems using the Pythagorean theorem and the trig ratios, but really that is only one select group of triangles. Well, today, all of that changes. Today, we are going to unlock the world of solving oblique triangles. An oblique triangle is any non-right triangle, or a triangle that does not have a right angle. Before this lesson, the tools we used to solve for the side lengths and angles in triangles only applied to right triangles. So if we were asked to solve this triangle, ABC, we'd be stuck. Well, thanks to 13th century mathematicians, we have the law of sines, which we can use to solve for missing side lengths and angles in any triangle. The law of sines states that in any triangle, the ratio of the length of a side to the sine of its opposite angle is the same for all three sides. We write the law of sines as a three-part proportion, with side lengths represented as lowercase letters and angles represented as uppercase letters. Let's see how this works. Consider the triangle ABC. We are given the measures of angle A, angle C, and side C, and asked to solve for the missing angles and side lengths. What should I do first? Well, I actually have two options. I could solve for angle B, or I could solve for side A, and it doesn't matter which one we choose. I'll go ahead and find angle B first. Since the angles of a triangle add to 180 degrees, I'll take 180 and subtract 22 and 18. So angle B is 140 degrees. Now, I can use the law of sines to write a proportion and find side A. Sine of 18 over 5 equals sine of 22 over A. Do you remember how to solve a proportion? To solve a proportion, we cross multiply. That means 5 times sine of 22 equals A times sine of 18. Now, divide both sides by the sine of 18 to solve for A. There are two things to note before we plug this in the calculator. First, we need to make sure our calculator is in degree mode. And second, to preserve as much accuracy in our answer as possible, we don't want to round more than once. So we should enter 5 times sine of 22 divided by sine of 18, instead of doing this calculation in 2 steps. So A equals 6.06126, which we can round to 3 decimal places as 6.061. If you didn't get 6.061 and your calculator is in degree mode, double check that you closed this parentheses here. There you have it. You just used the law of sines to find the side length of a triangle. Pause the video now and find side B. Sine of 18 over 5 equals sine of 140 over B. Cross multiply. Divide, and I get side B equals 10.401. Is that what you have? Notice when I solved for side B, I used angle C and side C to set up my proportion. I could have used A, but remember, I like my answers to be as accurate as possible. Since I rounded side A to get 6.061, using side and angle C will give me a more accurate answer. How about this example? Pause the video and solve triangle ABC on your own. Check your answers. How'd you do? Consider this example. Solve triangle ABC. What is our first step to solve this triangle? With the given information, we must solve for angle B first. We'll set up our equation as sine of 40 over 8 equals sine B over 10. Again, we cross multiply, so 8 times sine of B equals 10 times sine of 40. We'll divide both sides by 8, and now we get sine of B equals 0.803. How do we find the angle measure? To solve for an angle measure, I need to take the inverse sine of both sides. Inverse sine of 0.803 is 53.418, or just 53.4 degrees, when I round to the nearest tenth. But wait a second. You learned in Unit 5 that sine is positive in the first and second quadrants of the unit circle, which means that there is a second angle measure that would satisfy this equation for angle B. Welcome to what is known as the ambiguous case of the law of sines. Let's find out exactly what's happening with this triangle. So far, I already know angle B can equal 53.4 degrees. Now, what is the other possible measure of angle B? Well, let's go back to the step from right before I did the inverse sine. I have the equation sine of B equals 0.803. What other angle between 90 and 180 has a sine value of 0.803? I'm going to use 53.4 degrees as a reference angle to find which angle in the second quadrant also has a sine value equal to 0.803. Take 180 minus 53.4 degrees, and we get 126.6 degrees. This means that angle B could also be equal to 126.6 degrees. But how can we know for sure? It's time to revisit the triangles. Let's start with the first measure we found for angle B. If angle A is 40 and angle B is 53.4, angle C must be equal to 86.6 degrees. Do these angle measurements create a valid triangle? Yes, they do. So ABC is a triangle. Now let's look at the second angle measurement we found for B and see if it can also create a valid triangle. If angle A is 40 and angle B is 126.6, angle C must be equal to 13.4 degrees, which is also possible. That means there are two triangles that satisfy the given conditions that angle A is 40, side A is 8, and side C is 10. We can finish this problem using the law of sines to solve both triangles separately. Pause the video and do that now. In the blue triangle, angle B is 53.4 degrees, angle C is 86.6 degrees, and side C equals 12.424. In the orange triangle, angle B is 126.6 degrees, angle C is 13.4 degrees, and side C is 2.884. Before we do another example, let's summarize the process of finding two triangles with the law of sines. When given two sides of a triangle and a non-included angle, you need to consider all solutions that satisfy the given conditions. First, solve for the angle that corresponds to the given side. Next, use the angle from step 1 as a reference angle to find the measure of the angle in the second quadrant that has the same sine value. Then, use the triangle sum theorem to determine whether a second triangle is possible. If a second triangle is possible, solve both triangles separately. If not, solve the triangle using the first quadrant angle only. Look at this example of the ambiguous case. Pause the video and try it on your own using the steps we just outlined. Review your work with me. We need to start by finding the measure of angle B since side B is given. We calculate sine of 145 over 33 equal to sine of B over 7. Cross multiply and sine of B equals 0.122. Inverse sine of both sides, and angle B equals 7 degrees. Using 7 degrees as a reference angle, I subtract it from 180 to find the measure of angle B in the second quadrant with the same sine value, which is 173 degrees. Can we use this measure of angle B to create a second triangle? No. If the measure of angle C is 145 degrees and the measure of angle B is 173, angle A would be negative 138 degrees, which is not possible. So this second triangle is not possible. Since a second triangle is not possible, I will finish solving triangle ABC by going back to the original angle measure I found for B, which was 7 degrees. So that means angle A is 28 degrees and side A is 27.010. Take a look at this next example. Solve triangle QRS. I notice right away this is the ambiguous case because we're given two sides and the non-included angle. I set up law of sines to solve for angle S. Sine of 54 over 9 equals sine of S over 18. This gives me sine of S equals 1.618. But when I take the inverse sine of 1.618, my calculator says this is undefined. So, what's going on here? Well, I think back to Unit 5. Do you recall the range of the sine function? The range of the sine function is all values from -1 to 1. That means 1.618 is outside the range of the sine function. Since the inverse sine of 1.618 results in an undefined value, there are no triangles that satisfy the given information. So our answer is no triangle, or the triangle does not exist. You have now seen all three possible outcomes of the ambiguous case of the law of sines. The ambiguous case of the law of sines occurs when we are given two sides of a triangle and the non-included angle. This may result in 0, 1, or 2 triangles, as we've shown in the previous 3 examples. The sine function has one more trick up its sleeve. We can use the sine function to find the area of any triangle without needing an altitude or perpendicular height. The area formula you've used for triangles since grade school is 1/2 base times height, where height is a perpendicular measurement, which is not given in this triangle XYZ. Now that we know how to harness the power of the sine function, we can use it to solve for the area. Recall that the sine of an angle is the ratio of the opposite side and the hypotenuse, but that only works in right triangles. I will sketch an altitude from angle Y, creating a smaller right triangle that includes my given angle, 57 degrees. Using the sine ratio, I write sine of 57 equals h over 8. Then, solve this equation for h. H equals 8 times sine of 57, which I substitute into my standard area formula, 1/2 base times height, resulting in area equals 1/2 17 times 8 times sine of 57, which equals 57.03 units squared. Let's generalize this formula so we can use it for all triangles. In a triangle ABC, the area can be found by 1/2 side A times side B times the sine of C, which is the included angle, or more simply, 1/2 AB sine of C. Notice that we need two sides of the triangle and the included angle to use this area formula. Try this last example. Find the area of triangle DEF. Do we have enough information to find the area? Not quite. We need to find another side length. How can we do that? Right, law of sines. Use the law of sines to solve for side D, then find the area. Pause the video now. Review your work with me. I started by finding angle E since I need an angle and its corresponding side to use the law of sines. Angle E is 30 degrees. Next, I set up sine of 30 over 6 equals sine of 100 over D and found that D is equal to 11.818. Now I have enough information to use the area formula. Plug in the values, 1/2 6 times 11.818 times sine of 50. And I find that the area of the triangle is 27.16 units squared. How'd you do? Today, we learned that we can solve oblique triangles using the law of sines, which states that the ratio of the length of a side to the sine of its opposite angle is the same for all three sides. We discovered that the ambiguous case occurs when we're given two sides of a triangle and the non-included angle. And this can result in 0, 1, or 2 possible triangles using the given conditions. Finally, we discovered the area of any triangle can be found using area equals 1/2 A times B times sine of C. Make sure to complete the lesson activities and the online practice before moving on. See you next time. Hey.